In this video, we're going to consider the effect of fatigue on a very common design problem, that of shafts. So for shafts, we typically have a very consistent loading problem. If you recall, the whole derivation of fatigue really resulted from looking at what was happening with shafts. It's almost always the workhorse of the rotational world, and therefore it's where we see a lot of fatigue design problems starting from. So the first thing that we'll notice is that there's a fully reversed bending moment, and that bending moment is being created because of the weight of the shaft, and very often because of tension forces. So for instance, where belts and gears or chains interact with the shaft, there needs to be some sort of tension to make sure that the belts accurately transmit the power either onto or off of the shaft. In addition to that, we also have torques that are the main portion of the loads on a shaft. So consider that almost always shafts are being used to deliver power. So we have this equation that power is equal to torque times the speed of the shaft. And so there's always power being added to and taking away from the shaft. That's its purpose, is to transmit power, mechanical power. So sometimes the source can be variable. For instance, an internal combustion engine, you have torque being loaded onto the shaft by the pistons as they fire in the crankshaft. You also can have situations where the sink is variable. So for instance, if I have an electric motor that's turning a pump, the pump is really in some ways very similar to the internal combustion engine. There are parts of the stroke that are pushing and parts of the stroke that are pulling, and so you've got a varying torque over one rotation of the shaft. You also have cases where neither the source nor the sink is variable. For instance, electric motors driving a ball screw or something like that. And you have situations where both the source and the sink are variable. An internal combustion engine driving a pump would be an example of that. So this is going to be there's a lot of variation that's happening with the torque. Then also, less common, we have axial loads. We're going to try to avoid axial loads as much as possible, and we'll talk in later chapters about how to do that using different types of bearings so that the bearing holds the load and the shaft isn't actually being required to hold the load. But sometimes that's not completely possible. And when we have axial loads, it's almost always a weight. Maybe the shaft is running vertically, and so you have the weight of the shaft that's acting on it. And when that's the case, that means there's only going to be a mean and not an alternating component of the axial load. So let's look a little bit further about what kind of approximations and simplifications we can make to our fatigue analysis. The first one is almost all shafts are solid round shafts. At the end of this lecture, I'll talk a little bit about why that's the case, but that means that any place I see I, J, and A, I can go ahead and plug in what I know about solid round shafts. And rarely, but sometimes, hollow shafts are also used. So there's equations for that. Now, let's take a look at the solid shafts and let's see what the resultant stress is. Now keep in mind this is at a particular cross section and it's at a particular location on that cross section, which we've already discussed how to find those locations. I'm still going to have to analyze a shear and moment diagram and find the locations where the maximum stresses are likely to occur. But having done that, I can move quickly through the equations to figure out the von Mises stresses. So let's walk through that. So the axial component of the normal stress is going to only be dependent on the moment. That's what we've seen in all the problems we've done. So I can find the axial component of the moment. Now, recognizing that C is equal to the radius, the outside radius, that's where the maximum location occurs, that's where the maximum stress occurs, and recognizing the equation for I for a solid shaft, I can go ahead and directly get the shaft based off of my moment. So in this problem, if I have a moment that's given to me, and I understand the stress concentration that's happening, and I have the diameter of the shaft at that particular location, I already know the I already know the normal stress component that's alternating, caused by that alternating moment. I can do the same thing with the mean. For the torque component, it's going to be driven, the shear component is going to be driven completely by the torque. Again, we're going to assume it's a long enough beam we can neglect the shear force, so we won't even consider that in consideration. And again, I know R and J, so I can substitute those in and get another nice equation that has the alternating torque that will directly give me the shear, the alternating shear. And again, I can do that in the mean as well. So if I understand what the alternating and mean moment and shear are, and if I know the diameter of the shaft and I understand the concentrations that are happening, I can get these 4 stress components at that particular location. And then, like I said, in the rare case where there is an axial load, I can recognize that there's also a normal stress caused by the axial, and it's related. Again, I can plug in for the area, and it's directly related to that force, which most likely is going to be the weight of the shaft or something like that. Now, the equations are not quite so simple, but I can repeat the whole thing for solid shaft. And so here are equations as I plug in for I and C and R and J and A for hollow shafts. So this is nice. The next step is to find the von Mises stress. And to do that, I recognize that this is a 2D state problem. So sigma 2 is equal to 0 in this case. And I can go ahead and plug in what I understand about that directly. So these are very simple equations now. And again, I could go ahead and plug these in terms of M, the moments, and T, the torques, and F, the axial loads. Now, assuming that if there's any changes in the loading conditions, that they're going to be constant. And we've talked about some reasons why this is common, but for this class, we'll make this assumption. I can have the modified Goodman factor of safety equation. And now if I understand what the factor of safety I'm trying to achieve is, I have something that I can plug in. Notice that I'm using SN, and SN means this is the strength of the material at the number of cycles that I'm particularly interested in. So whether we're talking about infinite life cycles, then I would use SE. If we're talking about at the fatigue limit for something like aluminum that doesn't have an infinite life, I would use SF. And if I was talking about at 1,000 cycles, then I would find the strength of the material at 1,000 cycles, and that's what I would plug in for that SN value. Now, if I have a solid round shaft, very often what I'm trying to do as a designer is I'm given the material, I'm given the loads, and I'm trying to figure out how thick does the shaft need to be in order to not fail. If I make it too thick, it gets expensive to turn. If I make it too thin, we break it, and that's not good. So very often the diameter is what I'm trying to solve for. So a lot of work was done to simplify the equation, and it's not something I'd want to do every day, but it's not that difficult of an equation to solve all of these. But what I've got here now is the outside diameter, and again, this is only for a solid round shaft, but very often that's the case. So if I know the factor of safety, if I know my loading condition, if I know the material, so I know the ultimate strength, if I know the number of cycles I'm expecting the life to be, so I can find SN, then I can directly solve for the diameter with this one equation. And that might be handy for a lot of design applications. We could do the same thing with a hollow shaft. It won't simplify quite as simply as this, so I'll leave that. If we need to be doing a hollow shaft derivation, we might want to just do a guess and check approach, which is also a very valid solution technique. In other words, start from this equation here, pick a diameter, and then check to make sure that the factor of safety is what you expect it to be. If it's not, increase the diameter. So that's also a very common solution technique. Especially with a computer, I can automate the whole process and let it check a bunch of diameters and get back with me with one that's closest to my desire. So, Norton has a list in chapter 10 of the fourth edition of design considerations. And I'm going to walk through that list and talk a little bit more about some things to consider as we're designing shafts. The first one is short shafts are better than long shafts. If I have a short shaft, that means that the moment in the middle of the shaft will be less, unless it's a cantilever, if it's cantilevered at the end of the shaft. But the maximum moment will be less. So the shorter I can keep the shaft, the less stress I'm going to have. The less stress I have, the less deflection I have. So aim for short shafts if possible. Cantilever beams have larger deflections than simply supported beams. We saw that especially when we considered columns that buckled. We saw that a cantilever is a much worse of a design to prevent buckling than something that's supported on both sides. And that's the case with shafts as well. Whenever possible, it's better to support the shaft on both sides. Hollow shafts are superior in some ways in that they have a better stiffness to mass ratio. So they're more expensive to make, they're larger diametered, but if what I care about is lightweight shafts, that might be the way I need to go. We're considering every location on the cross section that might have a high stress. And so what I want to do is, I know if I need, for instance, to add a gear, and so I'm going to be stepping my shaft up to house the gear. I should do that, if possible, closer to the support and away from the middle of the beam, because I know that the maximum bending moment will be in the middle of the beam. So the further I can get away, the further I can move my stress concentrators away from the maximum bending stress, the bending moment, the better I'll be with my design. So there are some types of elements, matter of fact these next three, that are very deflection dependent. So for instance, gears need to mesh with other gears, and so there needs to be less than a total deflection of 0.005 of an inch and less than 0.03 degree deflection. So if I have a gear application, very likely at the end of the day I'm designing for deflection and not for stress. Plain sleeve bearings require less deflection than oil film bearings. We'll talk a lot about bearings in the coming lectures, so I'll leave that alone for now. Just recognizing again that sometimes depending on the bearing situation that I'm using, deflection becomes a driving factor in the design. And finally, the shaft slope for even roller bearings needs to be 0.04 for some types of roller elements. And again, we'll discuss that in detail about how to choose rolling elements. But just recognize that if I'm going to be using any sort of bearings, that probably means I need to be concerned about the deflection and the slope of the shaft. If I'm designing to prevent deflections, it's probably best that I use a low carbon steel. We've talked often in this course that that deflection has nothing to do with the strength of the material, it has to do with the modulus of elasticity. So a low carbon steel has all the modulus of elasticity that a high strength steel. And so typically if deflection is the driving factor, low carbon steel is appropriate to use. And again, we'll talk about different types of bearings and how to remove the load, but if I have an axial load on a shaft, I can support the axial load using an axial thrust bearing to do that. And that way, the thrust bearing is carrying the weight, and that the shaft doesn't have to carry the weight. But when I do that, I need to make sure that I take all of the weight down to ground at one location and not at two locations. Shafts very often are operating in higher temperatures, and if there's a thermal expansion, then the difference between the two thrust bearings might cause some issues. So in general, when we think about shafts and axial loads, we want every time an axial load gets built up, we want to support it with one thrust bearing. And then finally, I need to keep track a little bit of speeds. It's important that we find the natural frequency of the shaft. And then we need to make sure that the natural frequency of the shaft, which are the natural frequencies of real objects, are typically high. But we need to make sure that the first natural frequency is at least 3 times higher than the highest forcing function we expect. So if I'm running at 10,000 RPM, I'm now getting into the range where I might be near the natural frequency of the shaft, and so I need to check to make sure that that's the case. That's not the case. And we can do all kinds of things to change the natural frequency of the shaft if we need to, as well as just changing the design overall to reduce the highest forcing frequency that's expected. And as you can see in the slide, I would rather have 10 times the natural frequency. The natural frequency ought to be 10 times higher than the highest forcing frequency. So with these, we're now ready to consider some examples of shaft design, and that's what we'll discuss in class.